Imagine a world so massive it could swallow Earth dozens of times over, yet dancing around its star in less time than it takes for your morning coffee to cool. Welcome back, where we crack open the latest cosmic mystery that just dropped from the heavens. Today, we are diving deep into the discovery of NGTS 38b, a super Jupiter with an orbit so short, so wild, and so rare that it shatters our understanding of planetary formation. You will learn why this planet is a game changer for astronomers, what its strange 180-day cycle reveals about the early universe, and exactly how we caught it on camera. This isn't just another exoplanet story. This is the moment the sky finally whispered a secret it had been hiding for billions of years, and we are finally listening. Let's start with the sheer scale of what we are looking at here. We aren't talking about a rocky hunk of rock like Mars or even Earth. We are dealing with a super Jupiter. These are gas giants, massive enough to be considered rogue planets if they were wandering around in space without a star. NGTS 38b is particularly enormous, dwarfing Jupiter itself in terms of mass and size. But here is the kicker that makes this discovery so explosive. It orbits its host star every 180 days. To put that in perspective, Earth takes 365 days to go around the Sun. This planet completes a full revolution in less than half that time. This speed creates a gravitational tug-of-war unlike anything we have seen before. Because the orbit is so tight and fast, the star exerts an incredible pull on the gas giant, while the gas giant pulls back with equal force. This rapid movement suggests that the planet formed very close to its star in the early days of the system's history, and perhaps didn't migrate outward as much as we thought most giants would do. Usually, scientists believe giant planets form in the cold outer rings of a protoplanetary disk, where ice is abundant, then drift inward over millions of years. NGTS 38b seems to have stuck around tight, challenging that standard model. It's like finding a Ferrari parked in a snowstorm instead of on a desert track. It implies we need to rethink how these heavyweights assemble themselves in the chaotic nursery of star formation. Now, let's talk about what this means for the architects of our own solar system and others like ours. If NGTS 38b represents a planet that formed close to its star and stayed there, it forces us to reconsider the Goldilocks zone theory in a whole new light. We have always assumed that for a planet to survive without being shredded by tidal forces or eaten by the sun, it needs to be far enough away. But this discovery suggests that extreme environments can produce stable planetary systems if the timing is just right. Think about the formation of our own solar system. Jupiter and Saturn were definitely in the outer regions when they formed, but they migrated inward slightly before settling into their current positions. If a planet like NGTS 38b can exist stably on an 180-day orbit without being destroyed by stellar radiation or tidal disruption, it implies that the conditions for survival are more flexible than we gave them credit for. This opens up a whole new category of habitable zones not just based on distance from the sun, but based on orbital stability and gravitational balance. It suggests that there might be entire families of planets orbiting close to their stars, packed tight like sardines in a tin can, yet surviving for billions of years. This shifts the search strategy for life. Instead of just looking for Earth-like temperatures at certain distances, we might start looking for systems where massive gas giants are dancing closely with their suns, creating unique magnetic environments that could harbor smaller worlds protected by these giant shields. It's a paradigm shift from where is it cold enough to where is the dance stable enough, and suddenly the universe looks much more crowded and complex than we ever imagined. But how did we actually find this beast? This discovery wasn't made with a single telescope staring at one point for years. It was a triumph of global collaboration led by scientists from Queen's University Belfast, working hand in hand with the NASA Transiting Exoplanet Survey Satellite, or TESS. TESS is designed to scan large swaths of the sky looking for dips in starlight caused by planets passing in front of their stars. The transit method is elegant but tricky. You need the planet to align perfectly with our line of sight, every single orbit to catch even one glimpse. The challenge here was that NGTS 38b orbits so quickly, only every 180 days. In a typical survey, you might wait months or years for a planet to transit if it's in the outer solar system. But because this giant is rushing around so fast, the window of opportunity to catch it was incredibly narrow. The team had to process terabytes of data from TESS to spot that tiny dip in light against the background noise of millions of other stars. They also combined this with ground-based follow-up observations to confirm the mass and size, ruling out false positives like eclipsing binary stars, which can mimic a planet's shadow. This rapid confirmation process highlights a new era in exoplanet hunting, where speed is as important as sensitivity. We are moving from slow, deliberate discovery to an almost real-time analysis of cosmic events. It means that whenever TESS spots a potential anomaly, we can react with precision tools on Earth within days or weeks, not years. This agility allows us to catch these rare superjupiters before they drift away into the data void, preserving the golden moments where our best instruments align perfectly with the universe's most dramatic events. So, what does all this mean for the future of astronomy and our place in the cosmos? The discovery of NGTS 38b tells us that planetary systems are far more diverse than we ever dared to dream. It suggests that there is no single recipe for building a solar system. Instead, chaos reigns supreme, and stability is often the exception rather than the rule. This planet proves that massive worlds can survive in intense gravitational environments if they find their rhythm early on. For us, this is just the beginning. As our telescopes become more sensitive and faster, we will likely find hundreds, maybe thousands of such systems with similar tight orbits. We might even find smaller planets hiding in those same crowded neighborhoods, waiting for a transit to reveal themselves. Imagine finding an Earth-sized world sandwiched between two superjupiters, all orbiting at different speeds, but held together by gravity. The implications for life are profound. Perhaps the right conditions aren't about distance from the sun, but about the complex gravitational dance of multiple worlds interacting in harmony. This discovery also reminds us that we are witnessing a fundamental shift in how we view our solar system. We used to think we were unique in having such a structured, orderly arrangement of planets. Now we know there is a whole universe of chaotic, crowded systems out there, some with giants racing around at breakneck speeds. It humbles us and excites us all at once. The sky is not just a dark canvas. It is a bustling city of worlds, each telling its own story of formation, survival, and evolution. And now, thanks to the power of international collaboration and cutting-edge technology, we are finally starting to read those stories. That's our deep dive into NGTS 38b, a super Jupiter racing around its star in just 180 days and forcing us to rewrite the textbooks on planetary formation. It's proof that the universe is far stranger, more chaotic, and infinitely more fascinating than we ever imagined. If you enjoyed this journey through the cosmos, make sure to hit that subscribe button so you never miss a new discovery from our team. Drop a comment below telling me what other wild exoplanet stories you think we need to explore next. Thanks for watching, and keep your eyes on the sky. There's always something new waiting for us out there.